FabricPath mainly is going to be a layer 2 routing protocol. It's sometimes called MAC-in-MAC routing. And basically what it's going to allow us to do is to remove spanning tree protocol from the topology, which we know only allows us to do active standby load balancing, where normally we have our root port in spanning tree that's going up to the spanning tree root bridge. Then any other upstream ports are going to be in the blocking state. Then our downstream designated ports are going to be forwarding. But the devices on the remote end, likewise, they're going to have root ports and blocking ports facing upstream. So we're not going to be able to use all of the links at the same time. Now, even in the case that we're using things like virtual port channels or regular point-to-point port channels, we do still have some limitations as to how the load balancing can occur in the multipathing in the network, because those technologies are still going to be subject to spanning tree. And we saw this when we were looking at virtual port channels. With the VPC, we're using that to build a physical triangle topology, but then the end result is going to be a logical point-to-point link. So physically, the network is going to be a triangle from the downstream switch up to the VPC peers. Then, of course, between the VPC peers, we have that peer link and the peer keep alive that's helping us run the control plane behind the scenes. But the potential issue then is that we only can have 2 VPC peers. So VPC design is not valid when you have 3 or more peers. So essentially, your distribution switching blocks would have to be only 2 upstream switches, and then whatever your downstream access layer switches, like the 5Ks or the 2Ks, or maybe the fabric interconnects when we're talking about the unified computing system. But we still have that limitation of following the basic physical logic of 2 upstream peers from the VPC topology. Now, FabricPath is going to allow us to build essentially arbitrary topologies. So we could have a full mesh of our links, we could have any type of partial mesh, we could still be using the triangle topologies, or basically any way that we want to interconnect the devices. FabricPath is going to allow us to do that. And we'll see once we actually get into the implementation, it's very, very simple to implement. There's literally 4 commands total that we're going to be using to implement FabricPath. But behind the scenes, with the control plane protocols like IS to IS, for the layer 2 advertisement of the shortest path tree, it's going to simplify the end result, which is going to be the ultimate traffic forwarding in the data plane. So next I want to talk about some of the general terminology of FabricPath before we get into the specifics of how the feature actually works. And the first of which we have is what is now known as Classical Ethernet, or CE. Now, in the scope of FabricPath, Classical Ethernet is basically referring to what we would just normally think as of Ethernet. So it means the regular flooding rules for Ethernet, the regular spanning tree rules, the regular building block rules of how we have the point-to-point port channels, or in the case of VPCs, we have those triangle topologies. So in the case of FabricPath, we're now considering anything before that, kind of the legacy network, the classical Ethernet network. We then next would have what's known as the leaf switch for FabricPath. A leaf switch is going to be the physical box that is connecting the classical Ethernet domain to the FabricPath domain. So specifically with our devices we're working with here, this could be the Nexus 5500, it could be the Nexus 7K. There are going to be some specific hardware requirements of what design situations will or will not work with FabricPath. So leaf switch here, this is what's connecting the FabricPath domain to the regular classical Ethernet. We then have what's known as the spine switch, which is essentially a core switch in the backbone of the FabricPath domain. And the idea here is that it only has ports that are within the FabricPath network, as opposed to the leaf switch, which is going to have ports both in the classical Ethernet domain and in the FabricPath domain at the same time. So the leaf switch is kind of like the edge switch. The spine switch is going to be what's in the core. We then have what's considered as the FabricPath core ports. These are the ones that are either going from the leaf switch up to the spine, or from the spine switches to each other. And simply, this is going to be, from a configuration point of view, any of the ports that we issue the command switch port mode FabricPath on. So the classical Ethernet edge is going to be regular Ethernet down from the leaf switch to regular Ethernet. Then we're going to have the core ports that are facing from the leaf switch upstream towards the FabricPath spine switches. We then have the classical Ethernet edge ports. Like I said, these are going to be the downstream facing interfaces on the leaf switches going to the classical Ethernet domain. From a configuration point of view, essentially this is any link that does not have the switch port mode FabricPath command on. The next thing then is to understand how does the control plane work behind the scenes with FabricPath. So how does it actually exchange the routing information? How does it build the shortest path tree? How does it actually know how to route the traffic, since we're no longer using spanning tree for the root port, the blocking port, and the designated port elections? Now, FabricPath is based behind the scenes on what normally would be a layer 3 routing protocol, which is intermediate system to intermediate system, or IS to IS. So we're essentially going to be using IS-IS behind the scenes to do layer 2 routing, not layer 3 routing. And the goal of using IS to IS is that we're going to compute a shortest path tree, or the SPT, in order to figure out what are the valid paths between the nodes of the FabricPath network. Now, we'll see that there's going to be a key difference when we look at the behavior of FabricPath versus Overlay Transport Virtualization, or OTV, where both of these protocols, FabricPath and OTV, do use IS to IS in the control plane. But in the case of FabricPath, it is not used for the advertisement of MAC addresses. We'll see that with FabricPath, IS-IS is only used to build the shortest path tree between the nodes, so between the FabricPath leaf switches and the FabricPath core switches, or the spine switches. We figure out what are the different layer 2 routes that we can take. Then ultimately that is going to imply how we can layer 2 switch the MAC addresses or the regular layer 2 traffic over the FabricPath network. Now, from a design point of view, the reason that we would want to use IS to IS to do this is that we're trying to do layer 2 switching, so we don't want to have to rely on having a layer 3 transport. So IS to IS, for any of you that are familiar with it from a layer 3 routing point of view, you know that it has its own layer 3 transport. It is its own layer 3 protocol. It's part of the Connectionless Network Protocol, or CLNP or CLNS stack. It is not an IPv4 or an IPv6 protocol. So this means that we do not need to run IP in the core of the layer 2 topology. Now, if we were using IS to IS for regular layer 3 IPv4 or IPv6 routing, then of course we would need to have IP configured. It's going to be the same logic as if we were using OSPF for routing. But in this case, we're using it for routing layer 2 essentially over layer 2, or our MAC in MAC routing. Now, the other advantage of using IS-IS from a design point of view of the actual protocol is that it is natively extensible by what is known as the type length values, or the TLVs. Now, essentially the TLVs are arbitrary fields that are included in the IS-IS update, so in the actual link state packet exchange, where normally the TLVs would be where we encode like the IP route, the metric value. It can be used for things like MPLS traffic engineering that it has been extended in the past. But in this case, for the FabricPath application, the TLVs have been extended to advertise the FabricPath switch IDs, the FabricPath forwarding tags, ultimately to exchange the control plane information that's going to allow us to build the shortest path tree. So from a programmatic point of view, instead of reinventing a new protocol, we already have IS-IS. It already runs natively over layer 2, so we just need to define the new TLVs that are going to be used to advertise the control plane information between the leaf switches and the spine switches. Now, the other advantage here is that it also natively supports equal cost multipathing, or ECMP. And this is going to be the same logic as regular layer 3 IS-IS routing or regular layer 3 OSPF routing, because really at the core of their protocols, they're very, very similar. They both use the Dijkstra shortest path first, or the SPF algorithm, with the ultimate goal of building a shortest path tree to essentially build a graph of the network, figure out what are all the nodes, or normally routers in layer 3. In our case here with FabricPath, the nodes are going to be the layer 2 FabricPath switches. But this also means that we're not subject to layer 2 load balancing of spanning tree or port channels, or even the virtual port channels. So we can natively have equal cost paths, and essentially up to an arbitrary number of paths that we can load balance our layer 2 traffic flows between. So it takes what's already a tried and true mechanism of using IS-IS routing, same logic as OSPF routing, but now we're going to be applying it onto layer 2 routing for our MAC addresses, as opposed to our layer 3 routing of IPv4 or IPv6. Now, in order to allow this control plane to work, one of the important points that's introduced here with FabricPath is the notion of their switch identifier or their switch ID. Now, this would be analogous to the OSPF router ID or the IS-to-IS network entity title, the net address. Essentially, what the switch ID does is to identify the node in the IS-IS shortest path tree. So the goal of SPF is to programmatically solve what is the shortest path from node A to node B, C, D, E, F, G, etc. So all of the devices in the topology. So in order to do that, we need some sort of identifying number or field to figure out who are all the devices in the topology. Then from my perspective, I'm going to look at what is the metric or the cost of the links to reach those nodes. Then I can compute the shortest path tree and then ultimately use that for the layer 2 forwarding. Now, with the specific implementation of FabricPath, we really don't need to do anything in order to get this to work. The FabricPath switch ID is going to be automatically generated. However, in our case, we are going to be changing this just for the purposes of verification. Because otherwise, the switch ID is going to be basically like a pseudo-random field that's generated based on layer 2 information of the platform. But when we look at the IS-IS database and look at the actual routing exchange and the control plane exchange, it's going to make it a little bit easier to verify what's going on if we actually assign what this number is on a per node basis. So both on the leaf nodes and on the spine switches, or leaf switches and spine switches. So specifically, this is going to be the FabricPath switch ID command in global config. We're then going to use the show FabricPath switch ID to verify what are the different devices in the shortest path tree, and then ultimately figure out how are we routing our traffic towards them. The next portion would then be the data plane. So how do we actually send the traffic through the FabricPath network? Now, the key with this, since we are doing what is described as MAC in MAC routing, we're essentially doing layer 2 over layer 2 tunneling in the FabricPath network. So we're going to be receiving regular Ethernet frames in from our end stations, like our virtual machines or our access layer switches. And again, this is what we consider to be the classical Ethernet, or the CE domain. So we're going to be receiving frames in from the classical Ethernet domain, and then we're going to be performing an additional encapsulation. This is with the specific FabricPath header. Now, the key to understand here is that FabricPath is not Ethernet. And this is the reason why there is limited support on the hardware platforms of which devices can run FabricPath and which devices cannot run FabricPath. Because we're not doing Ethernet in Ethernet tunneling, we're doing Ethernet in FabricPath tunneling. So it's a proprietary frame format that Cisco came up with specifically for NXOS. It's not supported on any of the other platforms. And we do have some very specific hardware limitations of what can and cannot support the feature. So in the case of the Nexus 7000, we can only support this on either the F1 or the F2 modules, which again are our layer 2 only switching line cards, which means that when we're running FabricPath, we cannot also be doing layer 3 routing on top of those particular cards. Now, we talked a little bit about this before, some of the differences between F1 and the F2 line cards. As it stands with the current releases, if you're using F1 cards, those can be in the same virtual device context, or VDC, as M1 or the M1XL cards, or even the M2 cards. However, the F2 cards have to be in their own virtual device context, in their own VDC. So this means if you are using the F2 modules, generally F2 would be used on a FabricPath spine switch in the core, and is going to be used exclusively for FabricPath switching. It's not going to be running regular classical Ethernet at the same time, typically. Now, we also have support on the Nexus 5500, but we do not have support on the Nexus 5000. So the 5010 and the 5020 do not support FabricPath. The 5548, the 5596, the platforms that we're dealing with, those do support FabricPath. Now, additionally, this is a separate licensed feature, so it is not part of the base LAN or the advanced LAN package. So when we look at actually enabling this, if we don't have the license installed, we could use the licensing grace period in order to allow FabricPath switching. But this could be a design consideration, what the actual cost of the license is going to be for any devices that you want to run FabricPath on. Now, additionally, another key point to note here is that FabricPath is also not Trill. Now, Trill, or a transparent interconnection of lots of links, is a standards track protocol, or in some cases there are standardized versions of it already that have gone from draft to actual standard. But the trill feature is the same type of logic of FabricPath, or actually vice versa, that FabricPath is the same type of logic as trill, but the key is that FabricPath is a Cisco proprietary feature. Trill is the open standard equivalent, so the features are not interchangeable, they're not interoperable. The ultimate goal is going to be the same, that we're taking layer 2 traffic and we're tunneling it over layer 2, and we're using ISDIS to exchange the control plane information. But FabricPath doesn't really have anything to do with trill, other than the general analogy that we're trying to do MAC and MAC routing. Now, the way specifically that FabricPath routing is going to work is that the FabricPath header has a source address and destination address that is going to be the switch identifiers in the FabricPath shortest path tree. So as I mentioned with IS-to-IS, we're using the switch identifiers to define the nodes of the tree. We're building the shortest path tree between these switch IDs. Then we can use these source and destination fields in the actual data plane to tell the FabricPath core how the traffic is going to actually be routed. And this is the reason why it's described as the MAC and MAC routing, because we're doing that additional encapsulation. So ultimately, the traffic is going to be layer 2 routed via the shortest path tree. It's going to be the same type of logic as regular layer 3 IS-to-IS or regular layer 3 OSPF routing. And it would be analogous to single area or single level routing, single area routing in OSPF or single level routing in IS-to-IS. So we don't have hierarchy, there's no summarization. It's a fairly basic functionality of the link state protocols, but the end result is that we're able to do that layer 2 equal cost multipath, the ECMP. Now, specifically, if we take a look at the header format for FabricPath, we see at the top here we have a regular classical Ethernet frame, so our normal 802.3 or Ethernet 2 Ethernet header, where in the layer 2 header we would have the destination address, the source address, and then the ether type. The ether type is going to tell the layer 2 switch what is the next protocol in the payload. So for example, if we're using IPv4 routing, the ether type would be 0x800 to tell the actual processes that you need to take this frame and then move it up the stack from layer 2 to layer 3, because IP is going to have to process it. Now, in the case of FabricPath, we have this additional encapsulation on the outside. But one thing that is key to note here is that since FabricPath is implemented in hardware, on again either the F1 or F2 modules on the 7K or on the 5500, this additional encapsulation does not count towards the overhead of the underlying payload. So this means that if you're using normal Ethernet with an MTU of 1500 bytes, FabricPath does not require that you lower the MTU of the payload. Or in the case you're doing jumbo frames, either 9000 or possibly up to 9216, it means that you're not going to have to do any type of fragmentation. You're not going to have to do anything like editing the TCP maximum segment size between our client and server. Since it is implemented in the ASICs in hardware, it's natively going to account for that additional overhead that's happening in the actual layer 2 header. So if we look back here at the specific format, the key fields are that we have the outer destination address, or the ODA, and this is essentially specifying what is the destination switch that we are trying to tunnel towards, or essentially layer 2 route towards, in the FabricPath core. Then we have the outer source address, the OSA. This is the switch that actually took the frame from classical Ethernet and then did the FabricPath encapsulation, followed by the F tag, or forwarding tag, that is made up of a new ether type, 8903, which is also known as Data Center Ethernet, or DCE, followed by the forwarding tag and the time to live. Now, one of the key points when we talk about layer 3 routing versus layer 3 switching is that layer 3 routing natively has loop prevention mechanisms built into the actual data plane. And the way that this occurs with IPv4 or IPv6 is the time to live field. So every time I route a packet on a hop-by-hop basis, the receiving layer 3 router is going to be decrementing the TTL before it continues to forward it on to the final destination, or at least to the next hop intermediary device. So what this is going to allow us to do is to make sure that if there is a problem in the control plane, so if there's a routing loop and 2 routers end up pointing routes at each other, the traffic will bounce back and forth, but it's not going to bounce back and forth indefinitely. Now, in the case of normal classical layer 2 Ethernet switching, this is not the case. And that is the reason why we need spanning tree, to make sure that we do not form physical layer 1 or layer 2 loops in the network, because we could have packets like address resolution protocol that are used in the layer 2 broadcast and then would eventually loop infinitely around the network, because there is no time to live in the layer 2 header. So this is basically an additional protection mechanism that's built into FabricPath, that if something were to go wrong with the underlying ISDIS control plane, and there's some sort of temporary loop in the network based on the convergence, or what's sometimes known as a transient loop in the case of the link state protocols, the data plane in FabricPath is going to be able to account for this. So maybe ultimately the traffic gets dropped, but it doesn't mean that we're going to cause an infinite layer 2 loop in the network, which typically results in a network down emergency, that the CPU goes up to 100%, all of our links go up to 100% utilization, and then the network basically becomes unusable. But FabricPath is natively protecting against this by adding the time to live additionally in the new FabricPath header. Now we'll also see that there's some changes the way that FabricPath does its layer 2 flooding and the way that it does its layer 2 MAC address learning. Now FabricPath defines what we now consider as traditional MAC learning, where with traditional MAC learning of Ethernet, we have some frame that's coming into the layer 2 Ethernet switch. The layer 2 switch looks at the header, and based on that it knows what is the source MAC address and what is the destination MAC address. So I receive a frame in port 1, the MAC address in the source is A. I now know that MAC address A is located on port 1. So I'm using kind of a reverse logic in order to learn the MAC addresses of the layer 2 network. Now when I receive the frame, I now have implicitly learned the source address, but maybe I don't necessarily know the destination address. So in order to learn the destination address, I'm then going to flood the traffic everywhere. So this is why we have our unknown unicasts flooded as broadcasts, or our unknown multicasts flooded as broadcasts in the layer 2 network, because the idea is that we're trying to get a response to come back in from the destination, which implies that this would allow us to learn the source MAC address of what the original destination was. So based on this unknown unicast flooding behavior, this is how our normal traditional layer 2 Ethernet switches are able to build their MAC address tables or their CAM tables for layer 2 switching. Now in the case of FabricPath, we have a little bit change in this behavior, which is now known as conversational MAC learning. Now conversational MAC learning is not necessarily specific to FabricPath, but it was first introduced with this feature, and it's going to change a little bit the way that these switches insert the source MAC addresses into their CAM tables. Because ultimately, after the ISIS control plane is exchanged, we're still doing layer 2 switching. So we're not using IS to IS to advertise the MAC addresses. We still need normal layer 2 flooding, but what is going to change is how we actually learn the MAC addresses once they are flooded. Now the key of this conversational learning is that the FabricPath node is only going to learn the source MAC address if it already knows the destination MAC address of the frame. So it's a little bit difficult to wrap your head around what this really means from an actual data flow point of view. So we're going to take a look at some examples on the command line, look at what does normal traditional MAC address learning look like. Then when we change to conversational MAC learning with FabricPath, what is it going to actually change in the layer 2 CAM tables? Okay, but effectively what this is going to be is an optimization of the control plane for layer 2. It is not necessarily an optimization of the data plane, doesn't control how traffic is flooded, it is just controlling how the switches are inserting the MAC addresses into their forwarding tables. Now this conversational learning, this is going to be the default mode for the FabricPath VLANs, but we can technically use this outside of the scope of FabricPath by going to a VLAN and changing it from traditional MAC learning to conversational learning. And if we had a large layer 2 topology that we're running into an upper limit of the size of the CAM tables, this could be an optimization we can use to cut down on the amount of MAC addresses that each switch in the network needs to learn. Because traditionally with a flat layer 2 network, all switches, including the access layer switches, the distribution and the core, will have to know about every single MAC address in the entire layer 2 network. Now, this especially becomes a problem if we start to do layer 2 data center interconnect with something like dark fiber or VPLS or any transporter over MPLS that do not have built-in optimizations for MAC address learning. It means that if we have 2 separate data centers that are layer 2 connected, any switch anywhere in the topology will always have to know every single MAC address in all of the data center sites. So we'll get into this a little bit later once we start to get into OTV and look at how OTV is optimized for the layer 2 MAC flooding and the layer 2 MAC learning when we're trying to tunnel layer 2 over layer 3 on the DCI, on the data center interconnect. Now, another important point to mention here is that on the FabricPath leaf switches, where again the leaf switches are going to be the ones connecting the FabricPath domain to the classical Ethernet domain, these devices must be the root bridges of the CE VLANs. Now we'll see once we actually extend the VLANs over FabricPath, the FabricPath leaf switches are going to be the demarcation point of spanning tree. So spanning tree does not span over FabricPath, and that's one of the advantages of the new control plane with IS to IS, is that we don't have to have a large spanning tree domain, which means that our failure domain is smaller, which ultimately means that if there is a layer 2 failure, so if there's a layer 1 link cut or there's some sort of layer 2 crash, it means that the entire spanning tree network does not need to reconverge. So spanning tree is going to be isolated from the leaf switches down to just their individual classic Ethernet domains. Now, in order to allow this to happen, we need to make sure that the top of the spanning tree, or essentially the root, is always on the leaf switches. So this means that the leaf switches will essentially be running the equivalent of the spanning tree root guard feature on any of their classical Ethernet-facing links. So to solve this problem, basically what we need to do is just go to the FabricPath leaf switches and make sure that they have the lowest priority for a spanning tree. So typically we go to all the leafs. We say for all the VLANs that you're going to be using over FabricPath, they should have a priority of 4096, or technically you could set it to 0. So some low value that is going to guarantee that they are actually the root bridge of the spanning tree.